Hello and welcome back to another math video. Today we are doing a walkthrough of the proof that the sum of all numbers from 1 to n is equivalent to n times n+1 all over 2. So let's start with our base case as always, where we are going to prove p of 1. So n equals 1. So we're just going to put in a 1 for all values of n on the left-hand side and the right-hand side. So on the left-hand side we get 1. And on the right-hand side, we get 1 times 1 plus 1 over 2. So 1 plus 1 is equivalent to 2. And those 2's cancel, so you're left with just a 1. And we get 1 equals 1, which is a true statement, so our base case is true. So that's a great start. And then we are going to do our inductive hypothesis next, where we will assume p of k. So all we're going to do is plug in k for every single value of n in our claim. So 1 plus 2 plus 3 plus all the way to k is equivalent to k times k plus 1 all over 2. And then for our inductive step, we are going to prove directly p of k plus 1. And for our inductive step, we're going to plug in k plus 1 into both the left-hand side and the right-hand side of our claim. So 1 plus 2 plus 3 plus k plus 1 equals k plus 1 times k plus 1 plus 1 all over 2. And I think the side that I want to work on is the left-hand side. Technically, you can manipulate either side, the left-hand side or the right-hand side. It doesn't matter, but one of the sides is sometimes easier. So I'm going to choose the left-hand side. So when I'm looking at the left-hand side of this equation, what I'm seeing is that part of this equation looks pretty familiar. I'm going to take a second and let you think about it. But the side that looks pretty familiar, or part of this equation that looks pretty familiar, is this 1 to k plus 1 sum, which is exactly what we had in our inductive hypothesis. And using our inductive hypothesis in our inductive step is a pretty good sign that we're doing something right. So I already assumed that 1 plus 2 plus 3 all the way to k is equivalent to this equation, k times k plus 1 over 2. So I'm going to use that. So we're going to say k times k plus 1 all over 2. So that's replaced this part, and we still need to rewrite the rest of this equation. So plus k plus 1 equals the right-hand side. I'm not going to rewrite any of that, but you can pretend it's there. Maybe you want to rewrite it. That's totally fine. And I'm looking at my left-hand side of the equation and wondering what I want to do with it. And I think what I want to do next is put it all in one fraction. So I'm going to multiply this term by 2 on the top and by 2 on the bottom. So I can put the whole thing over 2. So I have k times k plus 1 plus 2 times k plus 1. That whole thing is over 2. And looking at this equation, I think I'm seeing a common factor, this k plus 1 in the term here, and the k plus 1 in the other term. So I'm going to factor that k plus 1 out, and we'll see what we get. K plus 1 times k plus 2 all over 2. And to me, that looks pretty familiar. I am seeing it's pretty similar to that right-hand side that we were trying to get to, but for you, maybe it doesn't. And so then let's take our right-hand side and let's simplify it a little. Let's see if we can make this a little more readable. And that right-hand side is equivalent to k plus 1. And then this is the term I mostly wanted to clean up. Times k plus 1, which is equivalent to just k plus 2 all over 2. And that is exactly what we simplified to on our left-hand side. So we know this left-hand side is equivalent to the right-hand side, and that is the end of our proof. And what that means for us is that we just proved that this statement is correct, because we already said the initial case was true, so it's true for p of 1, and we said that it was true for p of k, then it would be true for p of k plus 1, and we just did that by finding an equivalence between our two sides. That's all for this proof. Thank you so much for watching. I hope you learned something new. And as always, keep on trucking.